Thermal testing and verification. This lesson provides an introduction to spacecraft thermal testing and a comparison of the thermal test requirements and practices of different government organizations, including NASA's Goddard Space Flight Center, the Jet Propulsion Laboratory, and the Department of Defense. The Jet Propulsion Laboratory is a federally funded research and development center operated by the California Institute of Technology for NASA. Defense Department spacecraft test requirements are under the purview of the Air Force. Goddard, JPL, and Air Force specifications all provide well-documented and detailed requirements for spaceflight hardware testing. This lesson will explain the various kinds of thermal testing that is performed on spaceflight hardware and the objective of each type of test. The interdependencies of thermal testing and the spacecraft thermal design analysis process will be explored. Test facilities, test planning, and lessons learned will also be discussed. The lesson is broken into 5 parts. Part 1 discusses the purposes of thermal testing, test levels, and margins. Unit, development, and subsystem tests are covered in Part 2. Part 3 discusses spacecraft level testing. In Part 4 we focus on thermal test facilities and methods. And finally, in Part 5, we conclude with test planning, lessons learned, and a checklist of helpful hints for successful tests. A roadmap slide will be presented at the beginning of each part to place the material to be covered in that part within the context of the overall class. Part 1, Fundamentals of Thermal Testing. This part of the thermal testing and verification lesson will cover the purposes of thermal testing and the test practices that are commonly followed throughout the industry. Types of tests, test levels, and test margins will be discussed. The purposes of thermal testing and how various types of tests address those needs will be explored. The key objectives of thermal testing will be outlined, and the types of testing typically found in industry will be described. Next, the concepts of acceptance, qualification, and proto-flight testing will be introduced. Finally, the important role that margin plays in establishing test temperature levels will be discussed. Test purposes and practices. Thermal testing serves multiple purposes. It increases confidence in the design and workmanship, ensures successful operation in flight, confirms thermal modeling assumptions, and provides a means of baking out contaminants that are present on and in-flight hardware. The probability of mission success is enhanced by demonstrating the robustness of the design, verifying hardware performances within specification in-flight-like environments, and through measurements of critical performance parameters such as power dissipation. There are some variations to be found in the test philosophies that have evolved at different organizations within the aerospace community. NASA, DoD, and commercial practices have been developed that have been successful in meeting the needs of these organizations over many decades of successful spaceflight programs. While organizational test practices share much in common, there are differences driven by mission environments, unique versus high production hardware, customer risk tolerance, and historical experience. JPL, for instance, has a culture grounded in deep space missions involving long cruises with little temperature cycling, while Goddard Space Flight Center and DoD missions are primarily Earth orbiting. Understanding how test requirements are driven by customer test philosophy is necessary to ensure a successful test campaign. It's important to have a thorough understanding of the customer's test terminology, temperature cycling requirements, including the number of thermal cycles, temperature levels and dwell time, and thermal balance criteria. All of these will be discussed at various points during this lesson. Thermal testing has multiple objectives that are addressed in different test phases. These include environmental stress screening, performance verification, turn-on demonstration at extreme temperatures, verifying performance of the thermal control system hardware, verification of the thermal design through thermal balance testing, and baking out contaminants from flight hardware. We will now discuss the types of thermal tests commonly conducted on spaceflight hardware. Environmental stress screening subjects the hardware to physical stresses that force latent defects to become observable failures. This allows components to be repaired or replaced prior to usage in flight. Stress is introduced by subjecting the article under test to environments that are more severe than what is expected in flight. This is accomplished by soaking the hardware at extreme survival temperature levels and cycling temperatures to plateaus that are hotter and colder than expected in flight operation. Thermal testing is usually the last test in the overall environmental test sequence because defects and weaknesses introduced by vibration, acoustic, and shock testing are more likely to become apparent through full functional testing performed at extreme temperatures. Performance verification demonstrates that a unit, subsystem, or space vehicle can operate within specifications in a flight-like environment. Functional tests are performed in which equipment is exercised over operational scenarios during the temperature plateaus and transitions. A realistic temperature and vacuum environment is maintained during the test, plus applicable margin. Equipment operating voltage and power dissipation are varied over flight ranges. Performance verification tests may also include environmental variations for day-in-the-life simulations. The third type of test demonstrates that a unit can be turned on in a severe thermal environment and that performance is not degraded when the environment or unit temperatures are returned to operational range. Power on can occur at extreme temperature, changing temperature, temperature gradient, or extreme voltage conditions. It is typically performed at cold and sometimes hot survival conditions. Inspect performance is not required until the device returns to its normal operating range. Thermal balance testing is performed to verify the thermal model's capability for predicting flight temperatures. Hot, cold, and sometimes transient environments are simulated, while temperature and heater duty cycle data are gathered under steady state and, sometimes, transient conditions. The test data are then used to adjust thermal math models. The final type of test to be discussed here is bake-out. The objective is to outgas volatile chemicals present in the materials from which spacecraft components are constructed in order to minimize contamination of sensitive spacecraft components such as optics and radiator surfaces. Bake-out is typically, but not always, performed in a vacuum at temperatures above the normal operating range of the component. We will now turn our attention to the different levels of testing performed on spaceflight hardware. Testing is performed at different stress levels and for different purposes. The most common categories of test are qualification, acceptance, and Proto-Flight or Proto-Qualification, and development tests. In qualification testing, the emphasis is on verification of the hardware design and manufacturing process, not the workmanship. Qualification testing is performed in environmental conditions more severe than expected in flight and is performed on non-flight equipment. In acceptance testing, emphasis is placed on verification of workmanship and demonstration of flight worthiness, not the hardware design. Acceptance testing demonstrates the acceptability of each deliverable item and is performed on the flight hardware after qualification testing has been successfully completed. Proto-Flight testing is a compromise in which qualification testing is also performed on flight hardware. It reduces the schedule time and the cost of building non-flight qualification hardware. This form of test is also known as proto-qual testing or flight-proof testing. The thermal test environment is typically between acceptance and qualification levels. Development tests are engineering tests used to gain design information. They can occur at any point in the test sequence, but they typically occur before formal qualification and unit level testing because the objective is usually to gain information needed to develop the design of the units and the spacecraft. The kinds of thermal tests we have discussed so far can be performed on individual units, subsystems, payloads, or entire spacecraft, and if the government is the customer, there will be requirements for testing at each of these environment and hardware levels. Three main types of thermal tests are performed: thermal cycle, thermal vacuum, and thermal balance. They are often referred to by their initials, TC, TV, or TB. Each of these tests can be performed at all the test levels we have discussed so far. Thermal cycle testing consists of rapid temperature cycling at atmospheric pressure. It is commonly performed in a dry nitrogen atmosphere rather than ambient air to avoid condensation of moisture on the test articles. The primary objective of thermal cycle testing is environmental stress screening and may be extended to meet burn-in test requirements. Thermal vacuum testing is thermal cycle performed in vacuum. The primary objective is to demonstrate hardware performance, although it is also often used to satisfy thermal cycle test requirements. Thermal balance testing is usually conducted as part of the thermal vacuum test. The objective of the thermal balance testing is to gather data for thermal math model correlation and verification of the thermal design. In defining a test campaign, it is important to consider all the environments that the flight hardware will experience over its life cycle, from factory to launch site and through the end of its on-orbit mission. Temperature, humidity, and pressure ranges, and the number of temperature cycles are all important considerations. Some devices also have unique needs to consider. Batteries may require special cooling during ground testing. Heat pipes must be kept level during ground tests in order to work properly. Lubricants may degrade or migrate during long-term storage. Solar cells may require inspection after test, and transfer orbit environments may present a highly stressing condition for power subsystem components. Here we see a representative example of a thermal cycle or thermal vacuum test profile. The unit is cycled between hot and cold temperatures with functional testing and hot and cold starts performed at the plateaus. The first cycle may include excursions to extreme cold and sometimes hot survival temperatures. Full functional testing is performed on the first and last cycle, with more limited functional testing on other cycles. We will now discuss test margins, which are required to account for uncertainties and ensure hardware robustness. Test temperature levels are defined starting with the expected on-orbit operating temperatures. These expected levels come from predictions made with math models and take into account the various factors that drive hardware temperatures, including orbit thermal environments, spacecraft configuration and orientation, voltage and unit heat dissipation, surface finish degradation, eclipse, ascent, and transfer orbit conditions. It is important that the analysis only consider a realistic hot and cold combination of these factors, such that realistic predictions are made. Once realistic expected temperature range is established, margin is typically added to account for analysis uncertainty and to ensure that the hardware design is robust. That is, the hardware will not break or severely degrade if it gets a little hotter or colder than expected. The acceptance temperature range is the minimum range to which all flight hardware will be tested. It is established based upon thermal model predictions plus margin, or a default minimum temperature range. Default minimum acceptance ranges are typically driven by the need to adequately stress hardware in thermal cycle tests and may be considerably more extreme than what is actually expected on orbit. If a unit was previously qualified for another program, the existing acceptance range is generally retained and the spacecraft designed to maintain the unit within that range. This is because requalifying the hardware is usually more expensive than tailoring the spacecraft thermal design to accommodate the existing unit allowable temperature range. To ensure the flight hardware does not exceed its acceptance temperature during actual mission, most organizations require that margin be maintained between flight temperatures predicted by analysis and the temperature at which the flight hardware is acceptance tested. This is done through the use of analysis uncertainty margin and/or establishing allowable flight temperatures that limit the predicted temperatures to a range that is less severe than that used in the acceptance test. The Defense Department typically applies 11 degrees C analysis uncertainty margin between predictions and the acceptance test temperatures per mil standard 1540, while NASA typically applies allowable flight temperature limits that maintain 5 degrees margin between analysis and acceptance. NASA's Goddard Space Flight Center adds another 5 C margin for analysis uncertainty, which brings their total margin between analysis and acceptance to 10 degrees C, close to the 11 C margin required by Mill Standard 1540. At JPL, analysis predictions are allowed to go all the way to allowable flight temperature limit, with additional margin as a goal. Qualification testing is conducted at temperature levels well beyond the expected service temperatures and is performed on non-flight hardware. This wider range serves as the minimum temperature range to which the hardware must be designed. Designing and testing a unit to this wider range ensures design robustness, proves the design by exposing any design defects, demonstrates tolerance to degradation due to fatigue and wear, and proves compatibility with acceptance test temperature control tolerances. Qualification temperature ranges are established by adding a qualification margin to the acceptance temperature range. The Defense Department and NASA Goddard typically add 10 degrees C, while JPL adds 15 degrees C on the cold end and 20 degrees C on the hot end. Note that while JPL requires less margin between analysis predictions and acceptance test temperatures, they require significantly more qualification margin. Some organizations also specify a default minimum qualification range. For DoD, this is minus 34 to plus 71 C, with JPL requiring a very similar minimum range of minus 35 to plus 70 C. One important concept to be understood here is that qualification hardware is usually not flown because it has been exposed to excessive environmental stress during testing. Building and testing qualification hardware that will never be flown is expensive. Proto-Flight qualification testing offers a compromise in the test sequence in which qualification testing is performed on flight equipment. In this option, the severity of the test environment is usually reduced by using a temperature range which is between the acceptance and qualification ranges. NASA Goddard and DoD accomplished this by reducing the qualification margin over acceptance from 10 degrees C to 5 degrees C. The qualification margin, however, is not reduced for proto-qualification tests at JPL. Spaceflight hardware is often, but not always, tested to a wider temperature range over which the hardware must survive, but where full specified functional performance is not required. Such survival temperature limits may be established for cases where the unit is either on or off and are typically defined at the beginning of the program based on hardware design limitations. Survival temperature limits are often paired with turn-on temperature requirements. Turn-on is usually the cold temperature at which the unit can be safely turned on and is frequently the same as the cold survival temperature. The objective here is to avoid the need for spacecraft heaters to warm the unit to operating temperature prior to turning it on. Inspect performance is not required until hardware reaches operational temperature range. Turn-on limits are usually set at the beginning of the program and may restrict unit operation to a temperature range less severe than survival. A key factor that organizations must consider in developing their thermal test strategies is the fact that flight temperatures predicted by analysis are uncertain to some degree, even after thermal math models have been correlated to ground test data. These residual uncertainties are driven by things such as difficulties in accurately capturing complex view factors and radiation environments in analysis and tests, directional reflectance and emittance of real surfaces not being modeled, imperfect knowledge of surface properties, exclusion of cables and harnesses in analytical math models, inability to accurately predict joint and interface conduction, inability to accurately predict multilayer insulation, or MLI, effective emissivity, error associated with the nodalization patterns chosen by the analysts, and imperfect ground test simulation. Uncertainties tend to drop as the design of the spacecraft matures. In the project's early stages, system requirements are still being defined and potential development problems are not well understood. As project requirements are better defined and flow down to the thermal engineer, better analysis can be performed and the impact on the thermal subsystem better understood. Preliminary and critical design reviews represent key points of design maturity. Correlating the thermal math models to thermal balance test data is a major thermal milestone that significantly reduces, but does not eliminate, uncertainty. Once the thermal math models are correlated to actual flight data, residual uncertainties become very small. Margins required by government agencies mitigate the risks associated with flight hardware being exposed to greater than expected temperatures on orbit. For NASA, 5C is maintained between allowable flight temperatures, or AFT, and acceptance. NASA Goddard requires an additional 5C margin between analysis and AFT, while JPL suggests that as a goal. For components that are thermally controlled by active means, such as heaters or loop heat pipe radiators, a 30% excess control authority may be substituted for temperature margin. In other words, predictions can equal the acceptance test temperature in that case. For Defense Department programs, 11C is maintained between analysis prediction and acceptance temperature after models have been correlated to thermal balance test data. An additional 6C margin is required prior to thermal balance test where practical. If applying this additional margin causes a significant increase in thermal control mass or power, the requirement may be waived. Where active control is used, DoD allows 25% excess control authority to be substituted for the 11 degrees C margin. Commercial programs typically apply 5C margin between analysis predictions and acceptance. In the commercial environment, customers tend to see spacecraft as a commodity, with price being of greatest importance. They're willing to accept higher risks to minimize costs. Commercial programs also tend to use standardized spacecraft which have less one-of-a-kind hardware, more spaceflight heritage, fewer components, and are flown in the same orbits and environments. It is not uncommon for commercial satellite manufacturers to have flown dozens of similar spacecraft over periods measured in decades. The intent of the 11 degrees C analysis uncertainty margin required by MIL Standard 1540 is to have 95% confidence that acceptance temperatures will not be exceeded in the hottest and coldest flight conditions. This margin is to be applied to realistic, worst-case hot and cold analysis cases with no extra pad applied to analysis parameters. Parameters are to be stacked only if such stacking will actually occur in flight. For example, end-of-life optical properties with hottest orbit beta angle and winter or highest solar flux. If, on the other hand, the greatest spacecraft heat dissipation occurs at the beginning of life, that would not be stacked with end-of-life surface optical properties, because that would result in an unrealistic worst case. The 11 degrees C analysis uncertainty margin has its origins in a study conducted by Richard Stark in 1971. The study compared analysis predictions to test and flight temperature data for several spacecraft and found a 2 sigma or 95% prediction error of 11 degrees C for programs that use the thermal balance test to verify analytic predictions. The study also found a 17 degrees C prediction error for programs that did not use the thermal balance test. Donald Gluck in the late 1970s and John Welsh in 2009 gathered data for 9 additional missions and found similar prediction uncertainty. For cryogenic systems, margins are often applied as a percentage of the design heat load and decrease as the design matures. At the conceptual design stage, a margin of 50% is recommended. This may be gradually decreased to 25% after flight acceptance testing has been performed. Thermal margins on cryogenic systems may also be applied as temperature margin. However, as the temperature drops toward absolute zero, each degree represents an increasingly large percentage of the thermal balance, so margins expressed in degrees are reduced. MIL Standard 1540, for instance, requires 11 degrees C margin for non-cryogenic designs, which it defines as those operating above 203 Kelvin. This margin would gradually be reduced to 1 degree Kelvin for a device operating below 23 Kelvin. The figure shown on this slide provides a good illustration of the role that margin plays in the overall thermal management process. There are 2 principal and to some degree competing needs. The first is to keep all piece part junction temperatures, such as those of transistors and integrated circuits, low enough to ensure good reliability. The second is to enable wide allowable flight temperatures for electronic boxes in order to avoid the need for complex spacecraft thermal designs that add unnecessary costs to the program. Margin is added to this process at several levels to ensure design robustness. Starting from the piece part, margin is applied to the maximum rated junction temperature of the part to establish a derated junction temperature limit, which is typically higher for discrete parts such as a transistor than for more sensitive integrated circuits. Starting from the unit level, margin is applied between the allowable flight temperature of the electronics box and its proto-flight or design temperature as measured at the box baseplate. Inside the unit, there will be temperature rise from the baseplate up to the point where the piece part is mounted on the circuit board, as determined by worst-case analysis. An electronic part stress analysis is conducted at a temperature 10 degrees C above this level. All predicted piece part junctions must stay below their derated design temperature limits. There are several key takeaways from this first lesson. Overall, thermal testing helps ensure a successful mission by increasing confidence in the design and workmanship. Temperature cycling provides a screen for workmanship defects, while functional testing demonstrates that the hardware operates within specifications in a flight-like environment. Thermal balance testing validates thermal math models and increases confidence in the thermal design. We have also stressed the important role that margin plays in accounting for uncertainties and ensuring design robustness. This concludes Part 1 of this lesson. In Part 2, we will focus on unit, development, and subsystem testing.